Just kidding, Caroline. Just what's going on? We're gonna have our exam on Monday of next week, whatever day. What is today? The 12th?
12th.
Monday the 19th is exam 1, and that'll be open note. The only thing it isn't is open internet, so you might want to bring a calculator. Probably need that for a few problems.
Will we have to graph on the calculator?
No, you shouldn't need to grab. No. And so you're okay then?
Yeah.
Yeah. Cool. Is this okay with everybody? Everybody got like a basic function calculator that can do powers and logs. That would be the place to use it. And if you're concerned about using your calculator on the kinds of problems that we have in the review exam, we can talk about that this week, because today, howdy.
Howdy, sorry.
Oh, good. Today, I just want to talk a little bit about price, demand and supply, and basically equilibrium in the business sense. Pretty simple concept, but I want to at least have some business applications for some of the stuff we've been doing. And then answer any questions, maybe do a little practice with exponentials and logs, because we haven't really gotten to mess around with that. And then Wednesday is just a come prep day, so this is just open work day, we'll call it that. You can come here and consult with me if you're concerned about any particular things, if you think you got it all in order. And the way to know if you've got it all in order is to check out the practice exam that I posted. It's in the announcements in World Class. This is way longer than the actual the exam. This would take too long. So this is significantly longer to give you practice, that's all. So if this takes more than an hour, it should. This should probably take several hours. I usually write my exams to take about a half an hour if you've got your ducks in a row. Even in a 75-minute period like this, the exam will be intended to be half an hour long. Any things about this that you're concerned about, or that I can give you to help prep? Did you find my my videos I made on the exponentials and the logs? Okay, cool. All right. Any questions you all have? I've got a little bit of an agenda, but I want to find out if there's anything you wanted to talk about. And if you need extensions on any of the MyOpenMaths, everybody should get 100% on all that stuff, right? That's just crazy not to. So if you need time to do that, let me know. All right. You will let me know in private, perhaps, if that needs to happen, or maybe it doesn't. Well, let's do some practice and see where you're at with these logs. So let's say I invest. Let's do it in the most businessy scenario we can think of. I invest $1,000 in an account for 1 year. And the interest rate, the APR, so the interest rate for the year, that's not the APR. What is that called? APY?
I think it's APY.
APY is the one for the year, so the APY. And then the APR is the effective one that we actually get when we compound. Cool. So interest rate for the year is 5%. How much at the end of the year? And you will need a calculator for this, we all will. If compounded, let's start off, I'll give you a few minutes on this. Every 6 months, B every month, then C, continually. So continuously, and that's a whole different formula. Let's just see where we're at, and then we'll talk about this. So if you're kind of like, I don't even know where to start, like blank or something, and I'll give you a formula. That's the blank. So the amount that I have in my account after investing a principal, so this is the investment, and then I have 1 plus my interest rate, and this is in decimal form, so that's gonna be 0.05 here, divided by the number of compoundings per year, so n equals the number of compoundings. This is my interest rate, and then up here I have times n times, and I put a t up here, and this is the number of years. So this is compoundings per year, and then t is the number of years. And that's a great formula to have. Can anybody help me out if I have a continuous? Does anybody know that formula, continuous compounding? No, okay, cool, I'll help you with that. That is principal times e to the interest rate r times t, where t is again the number of years up there. So PERT is a famous formula for doing interest. Then let's do this, see what we get, and then let's talk about what we got. And what is the relationship between this and these two things?
And what does E represent, sir?
E is, can somebody help me with that one? What is E? It's Euler, okay, that's a lot of silence, here, I'll help out. Euler's number, and it is approximately 2.7, 1828, 1828, and that goes on and on. But you have special buttons on your calculator for that, and I can come help you. Let's find those. Because that's kind of what I want to do, is make sure we got all our stuffs in a row.
Okay.
Real quick, thank you. It's hard for me to see with my ancient eyes and stuff.
Okay.
There it is. You see that blue E to the X?
Okay.
That's the one you want.
What would be the, just because I'm curious,
Yeah.
give me like that, what would that be?
So that one is just a variable, I think, if you're using some of the programming features or something. Maybe it works the same, but the other one's safer. The other one's definitely it. Yeah, let's be safe, right? Not a time to be experimental. That's cool, that's good. All right, yeah, so let's do the first one, every 6 months. So how many times a year, if you're doing it every 6 months? There you go. Perfect. And this
Oh,
2
and
again.
it's the same.
Yeah, it's the same at the bottom there as on top, and then t is the number of years. So we're just doing 1 year, so times 1, so, or just 2.
Yeah.
There you go, yeah, you bet. Anybody got a number on this first one? I could, but it'd be nice to just have somebody tell me the answer. What you got, Jack?
I got 1050.625.
So if we round up, does that sound right? Yeah, Mace.
I'm sorry, I'm just a little lost.
It's okay. That's what we're here for.
The .005, like when you set up that equation, the N and T and the N underneath are the
These are the number of times that I compound per year.
Okay.
So since we're doing every 6 months, it's gonna be 2, then this one's gonna be, N is 12 here
Okay.
for this one, and then this one, you have to use this formula.
Okay, cool, thank you.
Does that sound right?
Yep.
Yeah, cool. Anybody else getting this? Yes, cool. Anybody got a number for number B for me, that 12 months, 12 compoundings per year?
1008.35.
1,080?
8.
1,080. Huh, it should be more than this.
I got 1051.162.
Okay, 1,051 point what?
162.
162, yeah, so 16 cents. Wait, so how did we get 1,008?
I don't know.
I'm
I
gonna
don't-
come
I
take a
don't
look.
have it
Let's-
anymore.
This is great. We'll debug this.
Oh wait, I know what I did. I forgot to put the 12 in.
That'll
I
do
forgot
it.
to.
That would do
Yeah.
it. Cool. And now you're getting this?
Yeah.
Okay, awesome. Mace, how are these computations going for you, friend?
I'm making sure I can still get A. I haven't done like the full version.
Absolutely, yeah, that's great. Take your time. We got time. Cool. So slightly more interest. Actually, not that much more interest. Shockingly little extra. Not even $1 more for 10 extra compoundings. And then if we do that at every single instant of the day, we get that number there. And what did we get for that?
We got 1,051.27.
That's crazy. Wow. Just a hair more. That's astounding. What does this mean? What am I talking about when I say continuously compounding? What does that mean?
The interest just continues to add up regardless. It's hard, like it's just continuously adding. Like
At every
it's-
instant,
yeah, every instant, yeah.
At every instant of the day. So it's this formula here. So this is kind of crazy. It's this formula where n, the number of compoundings, is going to infinity. Very strange. Who could be? Hello. Good to have you here. So this formula, if this part here goes to infinity and this part goes to infinity, and what I mean by that is just really freaking big. You tell me how big you want n, and I'll tell you something bigger. I can always make n bigger. So look at how weird this is. If I have this, let's just look at this really quickly, because this is a little bit of our first taste of calculus. What is happening to this quantity as n gets bigger? And that's what this means. When I write n goes to infinity, I just mean n gets bigger and bigger. What happens to that quantity?
That's smaller.
Gets smaller because you're dividing by a bigger and bigger thing. So this thing is headed to 0. This thing is headed to infinity. So when you look at this, it's kind of weird because it looks like you've got p times something that's getting close to 1, right? Because I got 1 plus something that's shrinking, and raised to the infinity. It seems like that should just be 1, but it isn't, because this is never truly 1. It's always a little more. So it's a very strange thing. And it turns out that as n goes to infinity, this thing turns into this quantity. that if you were to take this n and replace it with 1,000 here and 1,000 up here, you would get close to the truth. And this is the truth. But we can think of this as an upper limit on our investments, on possible value of the account.
Possible value you stand to gain? Or
Yeah, of the possible amount of interest that you could come up with. So if you take a look at this over here, Mace, that number turned into 1,051.27. That's the most you could ever hope at 5% interest to get out of this thing. No matter how many times a year they compounded, that's the most you could have. This is literally every instant of the day compounding, and that's still the best we can get. Which is pretty crazy that if you look at the difference between just twice a year and every single moment of the day, twice a year is fine. Now, if we had billions of dollars, this would make a difference. If this were $1 million, then we might care about that extra little bit right there, but.
which out of the three is most likely to be like considered like most useful in terms of
Most common would probably be quarterly. I don't know. We've all had different loans and interest bearing accounts. So like I feel like quarterly interest is pretty common. So 4 times a year. Has anybody had anything other than that? Of course, if you have a student loan, they're going to try to get as much out of you as possible. So that's probably every month, I would imagine. Any questions on this? Mace, did you get this worked and you were feeling good?
Yup. Thank you.
Louisa, you feel good?
Mhm.
Awesome. Cool. So let's look at the flip side. And if you haven't had a chance to watch the little video I made on exponentials and logs, there's 2 little videos, they're like 20 minutes each. Please check those out because there's just some problems you can work along with. And if you don't know where I'm talking about, it's just my YouTube page. You might want to subscribe just so you get notified when our class videos come up. Not because I'm trying to gain notoriety and fame. People don't even like my videos. I've got like 1 like out of 1,000 videos up there. And I'm not saying you need to like my videos, but if you did, I'd notice. That's all I'm saying. I'm just a man, just a mortal man. I need likes. All right, so let's talk about the reverse of exponentiation. And the way to express this, and I'll say this as I did in my video, because I like thinking of it this way. If I have something is equal to a number raised to a power, this is the key to understanding logarithms. This statement is the same as this statement that the exponent is the log base b of this thing. So right here, I would just have this on paper anytime I'm working with exponentials and logarithms. This right here tells you that a logarithm is an exponent. So when I look at this, I can say, oh, this is the exponent I need to raise b to get the thing right here. And that's what this statement says, that if you raise b to this thing, you get that number. So quick examples, couple quick examples. If I wanted to find the logarithm base 10, let's just do some, oh no, I already did base 10 in that video. Let's do something a little more interesting. I have 3 and a 27 here. So when I look at this, it says what number do you have to raise 3 to get 27? That's the answer. Well, here, let's do it like this so it's consistent. Can you do this one in your head? 3. So this log is just 3 because 3 cubed is 27. So when you see this stuff, it's really weird to think about. Translate it into the equivalent exponential statement. Let's try another one here. What about log base 3 of 1/9? You're thinking along the right roads, but how do you get fractions? What kind of powers give you fractions?
Fractions.
Negative. Also, that's also fractions, but also negative numbers. So notice that this thing here is the logarithm base 3 of 3 to the -2nd power. And sometimes it's hard to actually think about that. This is 1/3 squared. And negative exponent actually means that put me under 1. So this is just notationally meaning this. And so the exponent here is -2. So when your logarithm is a negative output, it's because there's a fraction that you're taking the logarithm of. Let's actually look at a logarithm graph really quick. So they all have this same look, and this might make this a little bit more sensible. If I were to graph out y equals log base b of x. Let's go for some low-hanging fruit. What is this quantity? Ask yourself, like, take a moment. What is the output when x is 1? What power do I have to raise b to get 1?
1.
Well, b to the first will give me b, so 0. So this is equal to 0 because b to the 0 equals 1. So always thinking in this direction. That's where my log graph crosses through. Now let's go back to the thing you said just a second ago, Mace. What's that one? What power do you have to raise b to get 1 solid? Because there's a hidden 1 there, right? So at b, so wherever b is out here, that's when this outputs 1. But otherwise, it looks like this. So a couple things to keep in mind here is that this quantity needs to be positive. And having this in your mind can be helpful from time to time, but notice that in here, the output is negative. So I'm gonna just write a little thing here. Negative exponents are needed to get numbers less than 1, to get fractional things. 1/b, 1/b squared, that kind of stuff. Any questions or anything you'd like me to talk a little bit more about? Because I want to use this stuff. And that's really the most important thing. Can you use this? Specifically in these kinds of problems that we have here. Let's talk about one special logarithm. So this is the general logarithm, but if we have the base, b is the number e, which is a weird ass number, it's that crazy 2.7 number, but this shows up all the time. We say that log base e of something is the natural log. Probably because I guess it shows up in calculus like all the time. It's the pi of calculus. That's my new thing. I started saying that this year, and I probably said it a couple times in here. So to write this with the proper notation, that word is notation, we write ln of whatever. And so this has a hidden log base e in it. That will become one of the most important things for us, that natural log. And so let's write an equivalent statement that the natural log, so I'm gonna write this statement there. Something equals the natural log of something else is equivalent to, now go to this statement up here. What's my hidden base? B is E. So this says that this thing is E to the triangle. So let's stop for a second. Let's see how good we can just play with this. So keep this in mind. This is all you need to answer a couple questions. What is the natural log of E cubed? So take a second and just pull that together. And it kind of hurts a little bit, and hopefully so, that's good. Because that means you're gonna figure something out. And if it helps, you can make these equations. You can say, well, that's equal to something, if and only if what? Somebody help me out here? You got this yet? It's like hold up fingers. Fingers yet. Still thinking? Okay, cool. Cool. What are you thinking? You already got it. You're just cranking. Keep cranking. That's good. Keep cranking. They kind of, that's a good way to think of it. Yeah, yeah, they're inverses of each other. So that's a better way to think of it. Yes. So you're saying that, Manny?
Yeah.
Yeah. Yeah. Is this stuff? Yeah, on the edge? Okay, cool, good. I'm glad we're talking about it. Good, good. Look at the box here. This is saying, what exponent do I have to raise e to get e cubed? 3. How do you get e cubed? What power do you raise it to? You raise it to 3. So the answer here is just 3 is the natural log of e cubed. Because e cubed, so look here, right? Come here, put it there, and then here you've got e cubed. What makes these the same? A 3 in that triangle box. Here's a good rule of thumb that Hannah was saying to me just a second ago. If I have natural log of e to the something, that is just that something. So they cancel each other in a way. They're inverses of each other. And similarly, if I have this, I also get the same thing. So they undo each other. What power do I raise e to get square? Well, it's this number. Now raise e to that power. Not surprising that we get square. So these things are kind of saying some very self-referential things. Let's talk about how to use these. How to use logarithms. The main use is to solve for an exponent. This is pretty much the only reason you would introduce a natural log. You've got a variable that's an exponent. So for example, solve 4 to the x equals 6. I'm gonna recommend you stick with natural log when you're the one asked to do logarithms, when you're asked to solve something like this. Get used to this. You've got a button for it on your calculator. You don't have to worry about the base or anything. So the plan is this. Take the natural log of each side. Notice I'm saying take, not multiply by. I'm taking the natural log of the left side, and that's equal to the natural log of the right side. And I've got some log properties that I need to use. So we have 3 log properties. And I'm gonna write them in terms of natural log. So the first one is natural log of something raised to a power. I can bring the power out in front. So this is bring powers out in front. The other one is that if I have a natural log of something times something else, if there's multiplication before I do the log, that turns into sum of those 2 things if I do each piece separately. And then we've got one more, and that is the natural log of something divided by something is the difference in those 2 things. So good properties to have, and we're gonna use the very first one the most. So this property here, this is the one you're probably gonna be using most of the time, because it's going to help me bring that X out in front. So this thing here, this dude can come out in front. That's property 1 out there. So bring it out in front. And then divide by natural log of 4. And that's gonna be some number. And we don't care a whole lot about what that number is, but let's just do it together to make sure that we can do this on our calculators. Oh, my phone, I can't do it on my calculator, because that's right there. Could someone do it for me, please? I'd be so happy. I'd be so grateful to you. I would give you jelly beans if you wanted. Nobody ever wants these jelly beans.
I got 1.29.
1.29, okay. Thank you. Let's see what the democracy starts to chime in here for us.
That's what I got too.
Same thing? Cool. Troubles getting that?
I don't know how I know about that.
Okay, so what I would do, are you cool with kind of what I was saying to get up to there?
Kinda, sure, yeah.
Do you want me to go through it again?
Yeah, sure.
Okay. So I want to find that exponent. So I know I got to use logarithms. So I take the natural log of this side and of this side, and I just wrote that out right here, that mace. Natural log of 4 to the x equals natural log of 6. Just reminding myself what I'm doing. Let me stop. Got this problem? 1x, just like almost automatically, I just apply that. Then I'm gonna use this property. Why did I do that? Because now I can bring that exponent out in front. So because I got a natural log, I could take that x that was there and just put him out in front. And then I divide it by this number on both sides. So now I've just got x times a number is a different number. So x is the quotient of those 2 numbers. So on your calculator, you're gonna type 6, and then you're gonna do the second. We wanna get to, oh, it's right there in front. So we don't need seconds, so 6, and then we say natural log. Well, ass backwards, sorry. Let's do natural log of 6. Cool, and then, yeah, parenthesis, divided by, then hit natural log again. Natural log of 4. Beautiful. Now hit enter. There we go. We got it, yeah. Good stuff. Anybody else need help on getting that 1.29? Can do that? Cool. So let me ask you a businessy question involving this stuff. Let's say I've got an account. So we have $1,000 in an account. Start off again. $1,000 investment. And we have continual compounding. So we have an interest rate, let's go back to the 5%. And continual compounding. So the formula we're using to figure out how much we have in there at each moment is this one. How long till we have 2,000? So how long till the investment has doubled? Take a minute and try to solve that problem. And we'll actually find kind of a cool rule, a rule of thumb that people use in investment, a doubling time. Does anybody know the rule of 72? You ever heard of this in your business classes? No?
Heard
Yeah,
of it.
yeah. So it's all because of this. That's the rule of 72 is we should see a 72 kind of pop up in here somehow. So my guess is it's gonna take like, let's see. Like 14 years to double? That's my guess, I think. We'll see. Set up, get that going for you in case you're unsure. We want to find T. Run to the restroom, I'll be right back. know. Nobody knows yet.
Oh, wait. Next question?
Yeah,
I don't know if I did it right, but I got 22.
22 years.
Yeah.
Okay, that could well be. I was trying to do this computation in my head, and I think I did a pretty bad job on it. So we'll find out. Did you?
I mean, I just graphed it, but I got 13.863. I didn't know how to do it another way.
Cool. My guess was like 14 or 12. What did I guess? 12.
14.
14. Okay, let's try it. Let's just do it together. So step one is I want to find this exponent. To solve any exponential equation, you've got to get everything into this form. So there's no numbers in front, there's nothing streaming around. The only way you can apply a logarithm is if you have single number raised to some expression equals a single number. So step one is divide both sides by 1,000. We get this. Now I can either take the natural log of each side, or I can use this equivalence. These are the same thing. So I can immediately just go from here. Look, in the square, I've got 0.05t. In the triangle, I got 2. So I can immediately figure out what 0.05t is. 0.05t is the natural log of 2. And so this number here, could somebody crank that up? I think it's like 0.72 or something. That's where this rule of 72 comes from.
The line 2 is 0.693.
Okay, well then I'm completely 0.693. Thank you, Anna. And so then t divided, or t is going to be 0.693 divided by 0.05. There it is going to come.
That's the 13.86.
13.8. Cool. So about 14 years to double. So I feel pretty good about my guess. Not bad. Yeah. I was using some made up bullshit, but it worked apparently. So pretty good. Is there any questions I can answer about that? All right. There's one last thing I want to talk about, and then I just want us to work through this practice exam. So you've got lots of good practice problems in there to do this kind of stuff. But the one thing we haven't really talked about is this very businessy application of supply and demand curves. And it's going to get much more advanced. But I thought, let's talk about this now. Let's introduce ourselves to these basic ideas. And this is pretty straightforward, especially for business folk. But let's say I've got, let me give you a little header here. Working with supply and demand curves. So what we mean here is what will be at a particular price, what is the demand, and how much will we supply at that point? So we've got a couple quantities. We've got Q, and I'll put a little sub D. This is the quantity demanded at price P. So let's say that's 600 minus 2P. So this is quantity demanded at price P. And the quantity we're going to supply at that price, so quantity sub S, Q sub S, is going to be 3P. This is the quantity supplied at price P. How much does it cost to manufacture, or I guess if we're setting a certain price, there's going to be money coming back from that, and depending upon that revenue stream, we can produce more. So here it's just saying that the quantity supplied is roughly 3 times the price that we've set for the item. And this is a little harder to look at, but the first thing you should do is plot these together. Plot these two things together. So the first one is, these are both lines, and they will be for quite a while until we can do some calculus. Each of these is a line, and so you need to be able to do a basic line plot. Get a couple of points and move from there. So notice that when the price is 0, the quantity, and we'll just put Q here for quantity, demanded is 600. And then when the price is 300, the quantity demanded is 0. Nobody wants to pay that price. So this line right here, this is my demand curve. And we call it a curve loosely. It will be a curve eventually. And my supply curve is just a factor of 3. So when I'm at 0, when the price is at 0, we will not be producing anything at price 0. When the price is 300, let's go all the way to where this thing became negative. People are gonna be demanding 900. So the demand will actually exceed the supply at that point. So let's say this is 900 up here. And I've just drew that line to help make this all a little bit clearer, like so. So this is Q demand, and this is Q supply. We want to optimize things. So we don't want to produce more than is demanded. We want things balanced just perfectly. And what we're trying to figure out is what price should we charge so that between producing things and the demand for those things, that we don't have a surplus and that we don't undershoot. So we have exactly the right amount for the consumer. So what we need right now is this equilibrium point. And so in this equilibrium point, this is where supply and demand become equal. How do we find that point? Besides, we could guess. That sounds like a pretty bad strategy. You're consulting with someone and you look at their stuff and you go, well, we're just gonna have to guess. Not impressive. What can I do here, my friends? I wanna find what is the optimal price, equilibrium price, Jack.
You set the equations equal to each other?
Exactly. So just set these two equal to each other and solve for P. So to find the equilibrium price, set Q demand equal quantity supplied, and solve for the price that gives us that equality. So here, we're gonna have 600 minus 2P equals 3P. Add the 2P to each side. Divide by 5, and our ideal price is 120 whatevers. We don't quite know what that price is. That could be hundreds of thousands, that could be nickels, but we'll just say dollars for the hell of it. So that is my equilibrium price. Pretty straightforward overall. I just wanted to make sure that we touched base on it. There's a couple other quantities here that I want to talk about. This is the slope of these things. So this is the slope of the supply curve. This is the slope of the demand curve. Those represent a quantity. Does anybody know what those represent? Business folk? What is the fancy business term for the amount the demand changes if the price goes up 1 unit. Or the amount the supply changes if the price goes up 1 unit. What do you call that in business when you look at the change in output when the input changes by 1 unit? Marginal? Does this sound right? Marginal? There we go. Yeah, you've heard this. It's just probably not in the, because I'm not a business guy, I'm talking about it mathematically, so it probably seems a little weird. But these slopes are the marginal demand, and this one is the marginal supply. And let's write out what those mean. So marginal, let's just in general, marginal for us will equal slope. And it's going to represent the amount output changes if input changes by 1, increases by 1. Jeez. That's a 1. That's a 1 right there. It's looking all weird. So let's do 1 together. I've got a couple written out here. Let's take these same things, but let's assume that the supply is bigger. How does that change things? So let's take the same demand function. So my demand function is going to be 600 minus 2p. What happens if the supply curve is steeper? What is our new equilibrium price? Let's just practice this. Oh wait, that is not steeper, is it? No, that is the same damn problem. There we go, sorry. Were you asking something, Jack?
No, I was just doing it in my head.
Oh, okay, cool, yeah. Kind of works out nicely,
Yeah.
so, you know. We get 100 for our equilibrium price. You would probably also want to know the corresponding quantities that came out. So over here, I could use either one of these functions. At 120, that is 360 units. Over here, when P equals 100, you can use either one of these. Our quantity is going to be 400. That's the amount demanded, that's the amount produced. So let us see, what did it do? It went up a little bit, because we can just produce more. Produce faster. How's this feeling, friends? Yeah? So that's it. That's all I wanted to present to you today. I wanted to talk about this stuff. Your job over the next week is to work through all these problems and make sure that you understand them. And remember, everything's going to be open note. So what I would do is have little examples of these written out, especially for stuff you're unsure of. Make yourself go through here, write a little example or notes to yourself on these various things. Keeping in mind, this is way longer than the actual exam. But I can guarantee you a couple things. There will be, there's a very good chance of a problem like every single one of these. Of course, I'm going to ask you to find the equation of a line, right? Make sure you can do that. Of course, I'm going to ask you supply and demand stuff like question 3. And absolutely, you will have to do interest stuff like problem 10. But you should be ready for anything on here. So let's get cracking. Wednesdays, come on in and work day. Optional. If you don't feel like you need my support, I'm not offended. I'm just here to support you, so. Does this sound good? Do you want to work a little today, or how are you all feeling? We could call it, we could work. Would anyone like to stay here and work? No. Okay, let's not. But I will. Does anybody want me to talk to him about anything? No? Okay.
I will Wednesday. I don't frankly have the time to today.
Okay, sounds
I
good.
have a lot of stuff out there.
That sounds great. Yeah, we all don't mind getting out early. So this is great, friends.
Oh.